The universe plays by its own rules, and sometimes it throws the rulebook out entirely. What if everything we think we know about space is just the tip of the cosmic iceberg? From black holes that shouldn't exist to galaxies spinning faster than physics allows, the cosmos is full of puzzles that leave even the brightest scientists scratching their heads. Today, we're diving into 30 jaw-dropping moments where space flat out refused to follow the laws of science as we understand them. Get ready for a journey through the weird, the unexplained, and the downright impossible, because out there in the void, the universe is rewriting the rules right before our eyes. Picture this: two spacecraft hurtling through the void of space, expected to follow the precise dance of gravity. Yet something was off. NASA Pioneer 10 and 11 were obeying Newton's laws at first, but then, mysteriously, they began slowing down more than they should have. It wasn't a tiny margin of error, it was a cosmic hiccup that made no sense. Even after accounting for solar wind, fuel leaks, or instrument glitches, the numbers still didn't add up. Scientists scrambled for answers. Maybe heat from the probe's power systems was radiating unevenly, nudging them off course. Or perhaps, and this is where it gets wild, there's an unseen force, something beyond our current physics, tugging at them. Some even floated the idea of modified gravity, where the rules we know break down at extreme distances. Decades later, the Pioneer anomaly remains unsolved. It's a reminder that space doesn't always play fair, and sometimes the universe leaves us with more questions than answers. But that's the thrill of it, isn't it? Because every mystery is a chance to rewrite the textbooks. Here's how the universe delivered one of the biggest plot twists in science history. For decades, astronomers assumed the cosmos was expanding at a steady pace or even slowing down thanks to gravity's pull. But in 1998, two separate teams studying distant supernova made an observation that sent shockwaves through astrophysics. The data didn't just confirm the expansion, it revealed something far stranger. The universe wasn't just growing, it was accelerating, as if some unseen force was pressing down on the cosmic gas pedal. This wasn't a small discrepancy. It shattered long-held assumptions about how the cosmos behaves. Enter dark energy, a mysterious, invisible influence making up roughly 68% of the universe's total energy. Unlike gravity, which pulls things together, dark energy seems to push space itself apart. The kicker: no one knows what it actually is. Some theories suggest it's a property of empty space itself, while others propose entirely new physics. What makes dark energy so baffling is how effortlessly it defies expectations. If gravity is the universe's brakes, dark energy is the counterintuitive force flooring the accelerator, rewriting our understanding of cosmic destiny. Will this acceleration tear galaxies apart in a big rip, or could dark energy change over time? For now, it remains one of the greatest unsolved mysteries, proving that even the vast emptiness of space is anything but predictable. One summer night in 1977, a radio telescope in Ohio picked up something that still echoes through the halls of astronomy. For 72 seconds, a signal blasted through the cosmos so powerful, so bizarre, that the astronomer who discovered it circled the data printout and scrawled a single word in the margin: "Wow." This wasn't static or a satellite glitch. It was a narrowband radio burst precisely at the frequency hydrogen emits naturally. In other words, it was the exact kind of signal scientists had theorized an intelligent civilization might use to announce itself. The kicker: it came from a seemingly empty patch of space near the constellation Sagittarius, with no stars or planets close enough to explain it. Theories exploded. Was it a message from aliens, a cosmic flare unlike anything we've seen, or something more mundane like a passing comet reflecting radio waves? Decades of follow-up searches turned up nothing. No repeat signal, no natural explanation that quite fits. Even the comet theory, proposed years later, had holes, the timing didn't match, and comets don't typically emit such focused, intense waves. What makes the WOW signal so haunting is its perfection. It checked every box for what an artificial signal should look like, then vanished without a trace. Was it a one-time fluke, a distant civilization's accidental transmission, or proof that space is still full of phenomena we can't even categorize? Either way, it stands as a cosmic postcard, one we've never been able to reply to. In the depths of space, something fires off bursts of energy so intense they outshine entire galaxies, but only for the blink of an eye. Fast radio bursts, or FRB, are among the most baffling phenomena in the cosmos. These ultra-powerful radio pulses last just milliseconds, yet in that split second, they release as much energy as the sun does in 3 days. What's even stranger? Most FRBs never repeat. Like cosmic one-hit wonders, they flash into existence and vanish without a trace. But a handful defy even that pattern, crackling across the universe multiple times, sometimes in predictable rhythms, other times at random. One famous repeater, known as FRB 1218, flares up like clockwork every 16 days, as if something or someone is flipping a switch. So where do they come from? Theories range from the dramatic to the downright speculative. Colliding neutron stars, supermassive black holes, or even highly magnetized stellar corpses called magnetars could be responsible. But some scientists have dared to ask the boldest question: could these bursts be artificial? Hypothetical alien megastructures like gigantic power transmitters might explain their staggering energy, though most researchers lean toward natural, if still unknown, cosmic processes. Here's the kicker: FRBs arrive with a telltale distortion, stretched out as they travel through the sparse gas between galaxies. This distortion is actually useful. It lets astronomers map the invisible matter scattered across the universe. So while we still don't fully understand what creates these cosmic lightning strikes, they're already helping us decode the secrets of deep space. Fast radio bursts remind us that even in the vast quiet of the universe, there are flashes of brilliance, literally, waiting to rewrite the rules of physics. And with every new detection, we inch closer to solving one of astronomy's most electrifying puzzles. High above the South Atlantic, there's a stretch of space so treacherous that astronauts brace themselves when passing through it. Satellites glitch, computers reset, and instruments flicker as if some invisible hand is tampering with them. This is the South Atlantic Anomaly, a cosmic danger zone where Earth's magnetic field mysteriously weakens, leaving anything in orbit exposed to a hailstorm of radiation. Think of it like this: our planet's magnetic field usually acts like a shield, deflecting deadly particles from the sun and deep space. But here, that shield wears thin, creating a funnel where radiation slips through. The result, a Bermuda Triangle effect in low Earth orbit. The Hubble telescope even powers down its sensitive instruments when crossing this region to avoid permanent damage. What's causing this? Deep beneath the anomaly, Earth's molten outer core behaves strangely, possibly due to dense rock formations distorting the magnetic field. Some scientists suspect it's an early sign of a rare magnetic pole reversal, a flip that hasn't happened in nearly 800,000 years. Others point to space weather, where solar storms amplify the anomaly's effects unpredictably. The real puzzle: the anomaly is growing. Over the past 2 centuries, its reach has expanded westward, and the magnetic field weakens by about 5% per decade. Could this silent threat one day disrupt global communications or expose astronauts to dangerous doses of radiation? For now, it's a stark reminder that even our own planet hides cosmic mysteries, and that space isn't the only place where the rules can bend. In October 2017, astronomers spotted something streaking through our solar system that sent shockwaves through the scientific community. It was the first visitor from interstellar space ever observed, a bizarre, elongated object later named Oumuamua. But this cosmic tourist had a secret. Instead of slowing down as it swung past the sun, it unexpectedly sped up as if some invisible force was pushing it forward. Gravity alone couldn't explain this strange acceleration. The usual suspect cometary outgassing didn't fit either. Oumuamua showed no signs of a tail or gas emissions, the telltale fingerprints of a comet. So what was nudging it along? One theory suggested solar radiation pressure light from the sun acting like a gentle cosmic wind. But calculations showed the object would need to be bizarrely thin, almost like a solar sail. Then came the wild card: could Oumuamua be artificial? Some scientists speculated it might be debris from an alien civilization, a discarded piece of technology catching sunlight like a sail. Most researchers leaned toward natural explanations, like hydrogen ice sublimating invisibly, but no single theory fully explains its odd traits. What's truly fascinating is how Oumuamua blurred the line between known and unknown. It didn't behave like an asteroid or a comet. It was something else entirely, and by the time telescopes could take a closer look, it was already racing out of sight, leaving us with more questions than answers. This interstellar mystery reminds us that space is full of surprises, and sometimes the most groundbreaking discoveries don't follow the script. Whether natural or not, Oumuamua proved that our cosmic neighborhood is far stranger than we ever imagined. The moon seems like a quiet, unchanging neighbor, a rocky relic of Earth's past with no surprises left to share. But buried in its ancient rocks lies evidence of something that shouldn't have been possible: a magnetic field. Unlike Earth, with its churning molten core generating our protective magnetic shield, the moon is far too small and geologically inert to power such a force. Yet Apollo mission samples revealed something astonishing. Billions of years ago, lunar rocks solidified in the presence of a magnetic field nearly as strong as Earth's today. So how did this happen? Dynamo theory: the same process that creates Earth's magnetism requires a hot, swirling core. But the moon's core is tiny and cool, making this explanation impossible without some cosmic loophole. Scientists have scrambled for answers. One leading idea points to colossal asteroid impacts in the moon's youth. A massive collision could have jolted the core into temporary motion, jump-starting a short-lived magnetic dynamo. Others suggest the early moon may have spun much faster, its rotation stirring molten layers deep inside like a celestial mixer, the most puzzling part. This lunar magnetism lasted far longer than these theories can easily explain, perhaps for over 1 billion years. Some researchers now propose that sinking minerals in the moon's mantle, cooling over time, may have kept the core churning far longer than expected. It's a reminder that even well-understood worlds can hide staggering secrets. What makes this mystery so thrilling isn't just rewriting the moon's history. It challenges our assumptions about how magnetism works on any rocky world. If something as small as the moon once held a mighty magnetic field, what other cosmic rules might we have gotten wrong? Every new lunar sample could hold the key to unlocking this ancient enigma, proving that even our closest celestial companion still has stories left to tell. The James Webb Space Telescope promised to rewrite astronomy textbooks, but no one expected it to do so this quickly. Among its earliest discoveries were galaxies so massive, so strikingly mature, they seemed to defy the very fabric of cosmic time. These ancient celestial cities, glowing in the darkness just a few 100 million years after the Big Bang, shouldn't have existed. According to our best models, the universe simply hadn't had time to build something so colossal. Take galaxy JWST 13-0, for example. It blazed into existence when the universe was a mere 300 million years old, a cosmic toddler by any measure. Yet its structure, its starlight, its sheer size all hint at a level of maturity that would typically take billions of years to develop. If the universe's timeline were a novel, this would be like finding a fully formed civilization in the prologue. Astronomers had two options: either their calculations were wildly off, or the laws governing galaxy formation needed a serious rewrite. Some theorized these early galaxies grew unnaturally fast, fed by rivers of cold gas streaming through the young cosmos. Others suggested that dark matter, the invisible scaffolding of the universe, might have clumped together differently than predicted, giving star systems a head start. The discovery sent shockwaves through cosmology, forcing scientists to revisit fundamental questions. Could black holes have jump-started galaxy growth? Did the early universe operate under different physics altogether? Every new Webb observation adds fuel to the debate, with some researchers even proposing radical ideas like a tired light theory, where light loses energy over vast distances, making these galaxies seem older than they really are. What's undeniable is that Webb has pulled back the curtain on a universe far stranger and more dynamic than we ever imagined. These impossible galaxies aren't just outliers, they're clues pushing us to rethink the cosmic dawn. And as the telescope peers deeper into the past, one thing becomes clear. The story of our universe is still being written, and we're only just beginning to read it. The silence of the cosmos might be the most unsettling mystery of all. With billions of stars in our galaxy alone, many hosting Earth-like planets, the universe should be teeming with civilizations. Yet after decades of searching, we've found no signals, no alien megastructures, not even a single microbe beyond Earth. This glaring contradiction has a name, the Fermi paradox, and it forces us to confront a chilling possibility. One explanation cuts deeper than the rest. The Great Filter theory suggests that somewhere between lifeless chemistry and galaxy-spanning intelligence, there's a near insurmountable barrier, a cosmic sieve that most life fails to pass. The terrifying question, is this filter behind us, meaning we've already beaten extraordinary odds to exist? Or is it still ahead, lurking in humanity's future as some inevitable catastrophe? Nuclear war, runaway AI, or even unseen astrophysical disasters could spell doom for advanced civilizations before they ever make contact. But not all theories are so grim. The zoo hypothesis flips the script. Maybe extraterrestrials are out there, deliberately avoiding us. Like anthropologists observing an uncontacted tribe, they might be waiting for humanity to reach a certain maturity before revealing themselves. Others suggest the vastness of space itself is the answer. Interstellar travel could be so difficult that even advanced societies rarely bridge the gap between stars. Then there's the haunting thought that we're simply too early. Complex life might be an ultra-rare latecomer in a universe still cooling from the Big Bang. Or perhaps we're searching all wrong, scanning for radio waves when advanced civilizations have moved on to technologies we can't yet detect. The Fermi paradox isn't just about aliens. It's a mirror forcing us to question humanity's place in the cosmos and whether intelligence, against all odds, is destined to flicker out before it ever truly connects. Every silent radio telescope carries the weight of that uncertainty, making the void between stars feel less like emptiness and more like a riddle we're desperate to solve. Here's how the universe performs its most bewildering magic trick. Imagine two particles born together, then flung to opposite ends of the galaxy. Change one, spin it, nudge it, measure it, and the other instantly changes too, as if they're whispering to each other faster than light should allow. This isn't science fiction, it's quantum entanglement, and it shreds our everyday notions of distance and reality. China's Mishi satellite turned this wild concept into a cosmic reality check. In 2017, it beamed entangled photons, particles linked by their quantum properties, to ground stations over 700 miles apart. When researchers measured one photon's state, its partner, hurtling through space at that very moment, mirrored the change immediately. No signal could have traveled between them fast enough to coordinate this. Einstein famously called entanglement spooky action at a distance, but Mishi proved it's a fundamental feature of the universe, not a ghost story. What makes this truly mind-bending is how it defies locality, the rule that objects can't influence each other faster than light travels. quantum mechanics doesn't just bend this law, it ignores it entirely. Some theories suggest entangled particles aren't truly separate at all, but part of a deeper, hidden layer of reality where distance is an illusion. Others speculate that gravity itself might play a role, with space-time acting as a silent conductor for these impossible connections. But here's the twist: entanglement isn't just a laboratory curiosity. It's the backbone of quantum encryption, where information can be transmitted with unhackable security. And if we ever crack quantum gravity, the elusive theory marrying quantum weirdness with Einstein's relativity entanglement might hold the key. Could space-time itself be woven from these invisible threads? Are we glimpsing the universe's underlying code? For now, entanglement remains a glorious mystery, reminding us that the cosmos operates on rules far stranger than fiction. And every experiment, from lab benches to orbiting satellites, pulls back another layer of the universe's ultimate magic show, one where particles dance in perfect sync, no matter how far apart they roam. Black holes don't just consume matter, they might be erasing the very fabric of reality itself. Here's the problem: quantum mechanics insists that information can never truly disappear. Every particle, every interaction leaves some trace behind, like a cosmic fingerprint. But when something falls into a black hole, Stephen Hawking showed that it radiates away over time as featureless heat. So what happens to all that intricate quantum information? According to the math, it simply vanishes. This contradiction is the black hole information paradox, and it's one of the fiercest battles in theoretical physics. Hawking radiation itself is bizarre enough. Empty space isn't actually empty, it's a seething quantum foam where particle pairs constantly blink in and out of existence. Near a black hole's event horizon, one particle might get swallowed while the other escapes, stealing a tiny bit of the black hole's mass in the process. Over eons, this slow leak would cause the black hole to evaporate entirely. But here's the catch: that escaping radiation carries no data about what fell in. It's like burning a library and claiming the smoke contains every book's contents. The universe's ledger seems unbalanced, desperate for solutions. Physicists have proposed mind-bending fixes. The holographic principle suggests that all the information swallowed by a black hole isn't lost, it's smeared across its surface like a cosmic DVD, encoded in 2 dimensions while the 3-dimensional interior is an illusion. Then there's the firewall hypothesis, a blistering wall of energy at the event horizon that vaporizes anything crossing it, preserving information but shredding Einstein's vision of a smooth, uneventful fall into oblivion. Each idea comes with trade-offs. Accept the holographic principle, and you're admitting reality might be a projection. Embrace firewalls, and relativity's textbook rules crumble. Some theorists even argue information escapes via hidden universes inside the black hole, a cosmic Hail Mary that rewrites the boundaries of space-time. What makes this paradox so thrilling isn't just the fate of stray atoms. It's a war between quantum mechanics and gravity, 2 pillars of physics that refuse to reconcile. Solving it might require a theory of everything, or force us to accept that the universe keeps its deepest secrets locked away, even from the boldest minds. One thing's certain: black holes aren't just cosmic vacuums, they're the ultimate puzzle, pressing us to question whether information itself is eternal, or if some truth really can be swallowed by the dark. The universe should be random, a vast, chaotic arena where matter scatters without pattern or preference. Yet hidden in the afterglow of the Big Bang, scientists stumbled upon something so unsettling they called it the axis of evil. It all traces back to the cosmic microwave background, the oldest light in existence, a fossilized snapshot of the infant universe. This radiation should be uniform, with tiny fluctuations spread evenly in every direction like static on an old television. But when researchers mapped it in detail, they found anomalies, strange, unexplained cold spots, and even stranger, these irregularities weren't randomly placed. They aligned perfectly with the plane of our solar system, as if the cosmos itself was tipping its hat to Earth in some bizarre cosmic coincidence. This alignment defies every expectation. The solar system is microscopic compared to the universe's scale, like a single grain of sand dictating the shape of an entire beach. Statistically, the odds of this happening by chance are astronomically slim. So is it a fluke, a systematic error in our measurements, or something far more profound, a crack in our understanding of cosmology itself? Some theorists suggest it's an illusion, a side effect of how we process cosmic microwave data. Others whisper about privileged frames of reference, an idea that turns modern physics on its head by implying Earth might somehow occupy a special place in the universe. The wildest proposals even tug at the fabric of inflation theory, wondering if the early universe expanded unevenly, leaving behind a hidden axis we're only now detecting. What makes the axis of evil so unnerving isn't just the mystery, it's the implication. If the universe isn't as isotropic as we've believed for decades, it could rewrite textbooks from the ground up. Perhaps space isn't the same in all directions. Maybe our solar system's quiet corner holds clues to a grander cosmic design, or worse, reveals we've been staring at the shadows on the cave wall all along. For now, this eerie alignment remains one of cosmology's great unsolved puzzles. And whether it's a measurement error or a glimpse beyond the standard model, one thing's certain: the universe has a way of humbling even our boldest assumptions. Some stars flicker gently like candles in the cosmic wind, but then there's KIC 8462852, better known as Tabby's star. This bizarre stellar oddity doesn't just dim slightly, it plunges by up to 22% at random intervals, as if something massive is passing in front of it. And when astronomers first saw the data, their minds raced to the wildest possible explanation. Could this be evidence of an alien megastructure? The idea wasn't entirely science fiction. Advanced civilizations might build Dyson spheres, vast networks of solar collectors encircling a star to harness its energy. If such a structure existed around Tabby's star, its irregular shape could explain the erratic dimming. For a moment, it felt like humanity might have stumbled onto the ultimate cosmic detective story. But space rarely serves up simple answers. Further observations revealed a more nuanced picture. The star's light dips weren't uniform. Some wavelengths dimmed more than others, suggesting fine dust, not solid megastructures, was the culprit. A vast swarm of orbiting debris, like comet fragments or planetary wreckage, could scatter starlight in unpredictable ways. Yet even this theory has holes. The sheer scale of dust required would dwarf anything in our own solar system, and the irregular dimming patterns still don't fully add up. Here's what makes Tabby's star so compelling. It refuses to fit into any neat category. Natural explanations exist, but none perfectly match the data. The dust theory, for instance, struggles to account for century-old observations showing the star has gradually faded over time, something no known cosmic phenomenon fully explains. Could it be a combination of factors, a dying star, a catastrophic collision's aftermath? Every new observation deepens the intrigue. Recent studies suggest the dust might be rich in carbon, giving it unusual light-scattering properties. Others propose a captured rogue planet torn apart by the star's gravity, leaving behind a sprawling debris field. But until we catch the star in the act, witnessing a major dimming event up close, the mystery endures. Tabby's star is a reminder that the universe loves a good plot twist. Whether it's dust, aliens, or something we haven't even imagined yet, this celestial enigma keeps us questioning, and that's where the real discovery happens. After all, the most exciting answer isn't always the one we expect, but the one that forces us to rethink everything. Physics has a golden rule: every action needs an equal and opposite reaction. So when engineers unveiled the M-Drive, a thruster that promised to push spacecraft without expelling any propellant, the scientific community braced for impact. This wasn't just bending the rules, it was tossing Newton's third law out the airlock. The concept seemed simple: bounce microwaves around a sealed, cone-shaped chamber, and the uneven pressure would somehow generate thrust. No fuel, no exhaust, just push. Initial lab tests, including experiments by NASA Eagleworks team, reported minuscule but measurable thrust, enough to send shockwaves through aerospace circles. Suddenly, the impossible looked tantalizingly real. Imagine spacecraft that could reach Mars in weeks, powered by nothing but electricity and ingenuity. But here's the catch: if the M drive worked, it would rewrite centuries of physics. Energy couldn't just appear from nowhere, yet the device appeared to create motion without any apparent reaction mass. Skeptics pounced. Maybe the thrust was an artifact of experimental error, thermal expansion, magnetic interference, or even subtle vibrations misleading the sensors. When researchers replicated the tests in harder vacuums or with tighter controls, the effect often vanished or became statistically insignificant. The final nail came from a brutal truth: no one could explain how it worked. Peer-reviewed studies either found flaws in the methodology or concluded that any observed thrust fit comfortably within the margin of error. Even the quantum vacuum theories proposed as loopholes crumbled under scrutiny, failing to account for the law of conservation of momentum. Yet the M drive's legacy lingers. It's a case study in how science should work: claims met with skepticism, tested relentlessly, and ultimately weighed against the unbreakable laws of nature. Sometimes the universe's answer is a firm no, but the pursuit of the impossible, that's where the next breakthroughs are born. Here's an invisible cosmic tug of war happening right now, and we're caught in the middle. Hundreds of galaxies, including our own Milky Way, are being pulled toward something massive lurking beyond the stars. Astronomers call it the Great Attractor, a mysterious region of space with gravity so intense it bends the motion of entire galaxies, yet we've never seen it directly. Why? Because it's hidden behind the thick dust and stars of our galaxy's own spiral arms, like a cosmic puppeteer working in the shadows. When scientists first mapped galaxy motions decades ago, they noticed something unsettling. Everything in our galactic neighborhood was streaming toward a single point in the constellation Centaurus at over 1 million miles per hour. The problem: there wasn't enough visible matter there to explain the pull. So what's lurking in that direction? One possibility is the Norma cluster, a dense supercluster of galaxies with enough collective mass to tug on us. But even that doesn't fully account for the staggering force at work. This leaves two spine-tingling options. Either there's an unfathomably large concentration of dark matter, the invisible glue holding galaxies together, or something even stranger is out there. Some theorists speculate the Great Attractor might be the heart of the Laniakea supercluster, a cosmic web where filaments of galaxies converge like rivers flowing into a waterfall. Others wonder if we're seeing the fingerprints of exotic physics, where gravity behaves differently on scales larger than we've ever tested. The irony. As we're pulled toward this enigma, the accelerating expansion of the universe means we may never reach it. Dark energy's relentless push could eventually overpower the Great Attractor's pull, leaving its secrets forever out of reach. But for now, every new sky survey peeks a little deeper through the Milky Way's dusty veil, inching us closer to understanding the force that's steering our corner of the cosmos. One thing's certain: the universe loves a good mystery, and the Great Attractor is proof that even gravity, the force we think we know, still has surprises up its sleeve. Whether it's dark matter, hidden superclusters, or something beyond our current physics, this cosmic anomaly reminds us that the biggest discoveries might be lurking just out of sight. Neutron stars are cosmic metronomes spinning with such precision that their pulses rival atomic clocks. But every now and then, these stellar remnants do something utterly bizarre. They speed up without warning, as if hitting an invisible cosmic turbo button. Astronomers call these sudden jumps glitches, and they're one of the strangest behaviors in the universe's playbook. Take the Vela pulsar, for example. This neutron star, no wider than a city but weighing more than our Sun, typically rotates 11 times per second like clockwork. Then, in 2016, it abruptly spun faster by a fraction of a millisecond, a tiny change but enough to send theorists scrambling. If neutron stars are supposed to slow down over time as they bleed energy into space, how could one suddenly gain speed? The answer might lie in their alien interiors. Imagine a neutron star's crust, a rigid lattice of atomic nuclei floating atop a bizarre quantum ocean. Beneath the surface, protons and neutrons break down into a swirling superfluid, a frictionless state where matter flows without resistance. Occasionally, vortices in this superfluid may snap like elastic bands, transferring angular momentum to the crust in a cosmic jolt. Think of it like a figure skater pulling their arms in suddenly to spin faster, except here, the skater is a city-sized star with physics-defying density. But there's another contender, starquakes. Neutron star crusts are under unimaginable strain, and like tectonic plates, they can fracture under pressure. A sudden crack might cause the star's surface to shrink slightly, making it spin faster to conserve momentum, just as an ice skater spins quicker when they tuck their arms in. Here's the twist: some glitches don't fit either explanation neatly. A few neutron stars slow down before speeding up or show delayed recoveries, hinting at even stranger dynamics beneath their surfaces. Could magnetic fields play a role, or is there some exotic phase of matter we haven't discovered yet? Every glitch is a cryptic message from nature, scribbled in the language of extreme physics. And with each one, we're reminded that even the most predictable objects in the cosmos can still surprise us, spinning mysteries into the fabric of space itself. Here's a cosmic puzzle that's keeping astronomers up at night. When we measure how fast the universe is expanding, we get two different answers, and the gap between them is too big to blame on simple error. It's called the Hubble tension, and it's forcing scientists to question whether we've misunderstood gravity, dark energy, or even the very fabric of the cosmos. On one side, we have the cosmic microwave background, the afterglow of the Big Bang. By studying its subtle fluctuations, astronomers calculate an expansion rate around 67 kilometers per second per megaparsec. But when we measure nearby galaxies using pulsating stars called Cepheids or exploding supernova, the number jumps to 73. That 6-unit gap might sound small, but in cosmology, it's a chasm. Imagine measuring the speed of a car with two radar guns. One says 67, the other 73. You'd assume one was broken, but in this case, both methods are rigorously tested, and neither shows signs of malfunction. So what's really going on? Some theorists suggest an unseen ingredient like dark radiation, or an early form of dark energy might have tweaked the universe's expansion in its youth. Others wonder if gravity itself behaves differently on cosmic scales, bending the rules we thought were set in stone, the most tantalizing possibility. This tension isn't a flaw in our measurements, it's a clue. Just as the orbit of Mercury revealed Einstein's theory of relativity, the Hubble tension might be pointing toward physics beyond our current models. Maybe dark energy evolves over time, or perhaps there are hidden dimensions subtly influencing the cosmos. Every new observation sharpens the mystery. JWST recent infrared eyes have scrutinized Cepheids with unprecedented precision, only to confirm the higher local rate. Meanwhile, upcoming gravitational wave detectors could offer a third, independent measure. One thing's certain, the universe isn't just expanding, it's expanding our understanding, forcing us to rewrite the cosmic playbook one contradiction at a time. Our universe keeps a shocking secret: nearly half the ordinary matter that should exist has gone missing. Not dark matter, not exotic particles, but the same protons, neutrons, and electrons that make up galaxies, planets, and even us. Scientists call this the missing baryon problem, and for decades it's been one of cosmology's most glaring blind spots. The math is straightforward. Based on the Big Bang's afterglow and the universe's initial chemistry, there should be twice as much normal matter as we've actually detected. So where is it hiding? One leading suspect is the warm-hot intergalactic medium, WIM for short. Picture this: vast, diffused threads of superheated gas weaving between galaxies like a cosmic spiderweb, too faint to see with traditional telescopes. These filaments, heated to millions of degrees, emit X-rays so subtle they've eluded detection until recently. Cutting-edge tools are finally lifting the veil. ESA's XMM Newton and NASA Chandra telescopes have begun spotting faint X-ray glows from these elusive structures. Even more striking, astronomers used distant quasars as backlights, detecting the fingerprints of oxygen ions in the WIM tendrils like finding shadows cast by invisible smoke. But the mystery deepens. Some models suggest these filaments might not account for all the missing matter. Could rogue gas clouds lurk even deeper in cosmic voids? Or might some baryons exist in exotic states we can't yet measure? Every new observation chips away at the enigma, proving that sometimes the universe's greatest tricks aren't in what it shows us but what it hides in plain sight. This isn't just a cosmic scavenger hunt. Solving the baryon problem could reshape our understanding of how galaxies form, how the universe's large-scale structure evolved, and even how the cosmic web distributes the very stuff we're made of. The answer might be floating right between the stars. We just needed the right tools to see it. Deep in the constellation Boötes lies a cosmic desert so vast it defies logic, a yawning expanse of nothingness stretching over 300 million light-years. This is the Boötes Void, a region so eerily empty that if our Milky Way sat at its center, we wouldn't have discovered other galaxies until the 1960s. Most voids in space are like bubbles, but this one's a gaping chasm containing only a handful of galaxies where thousands should thrive. How does something this empty even exist? The standard model of cosmology suggests matter should clump together in a web-like structure, with filaments and nodes, not voids this extreme. Statistically, the Boötes Void shouldn't be possible, yet there it sits, a ghostly fingerprint on the universe. Some researchers argue it's just a rare fluke, an outlier in an otherwise uniform cosmic web. But others wonder if it's a sign of something deeper, anomalies in dark energy's behavior, or even relics from the primordial universe that sculpted space itself in ways we don't yet understand. Here's where it gets stranger. The few galaxies inside the void aren't just sprinkled randomly. Some cluster in tiny groups, as if huddling for warmth in the cosmic dark. One theory suggests they're survivors, clinging to wisps of dark matter that avoided being swept away in the void's formation. Another proposes the void isn't entirely empty, just filled with a form of matter so diffuse it evades detection, like a whisper lost in the static of space. What makes the Boötes Void so unnerving isn't just its emptiness, it's the questions it forces us to ask. Are we seeing a statistical hiccup or a crack in our understanding of how the universe builds its grand architecture? Future telescopes like the Vera Rubin Observatory might finally settle the debate by mapping fainter galaxies hidden in the void's shadows. Until then, this cosmic desert stands as a humbling reminder. Sometimes the most profound mysteries aren't in the stars but in the spaces between them. Mars should be a dead world, a frozen desert where the air is thinner than Earth's highest mountains. Yet something keeps stirring the pot, releasing bursts of methane gas that vanish almost as quickly as they appear. These mysterious spikes have scientists locked in a fierce debate. Is it the whisper of hidden life or just the planet playing geological tricks on us? NASA Curiosity rover has sniffed out the evidence firsthand. Trapped in Gale Crater, it's detected methane levels that unpredictably soar, sometimes 10 times higher than background levels, before dropping back to nothing within days. On Earth, that kind of pattern often points to biological activity, like microbes digesting minerals beneath the surface. But Mars isn't giving up its secrets so easily. When Europe's Trace gas orbiter scanned the same regions from space, it found almost nothing. How could an orbiting satellite miss what a rover on the ground keeps catching? One possibility is timing. Methane on Mars might dissipate faster than expected, broken apart by ultraviolet light or chemical reactions in the soil before it can spread high enough for orbiters to spot. There's also the chance that Curiosity itself is stirring up ancient methane trapped in rocks, releasing localized puffs that vanish before they reach the broader atmosphere. But the plot thickens. Some researchers argue the methane could come from purely geological processes like serpentinization, a reaction between water, rock, and heat that produces methane abiotically. Mars has plenty of the right minerals for this, and its volcanic past might have left pockets of heat deep underground, cooking up gases even today. Then there's the thrilling wild card: what if it's both? Life and geology could be working in tandem, with microbes metabolizing the very chemicals these reactions produce. Until we drill deeper or bring samples home, the methane mystery remains a tantalizing riddle. Every new detection rewrites the story, keeping us guessing whether the red planet's whispers are just echoes of a lifeless past, or the first hints we're not alone in this barren, beautiful wasteland. What if centuries of human history never actually happened? That's the bold and wildly controversial claim of the phantom time hypothesis. This fringe theory suggests nearly 300 years of the past were invented, stitching the years 614 to 911 into an elaborate fiction. If true, it would mean Charlemagne never ruled, the Dark Ages were misdated, and our entire celestial timeline is off by generations. But could a conspiracy this vast really slip through the cracks of time? Proponents point to inconsistencies in medieval records and architectural styles that seem to leap forward without clear evolution. They argue that powerful rulers or the church might have fabricated history to extend their reigns or align events with prophetic timelines. The idea gained traction when a German historian noticed gaps in eclipse records from the era events that should have been meticulously documented but appear suspiciously absent. But here's where science pushes back hard. Tree rings don't lie. Dendrochronology, the study of ancient wood growth patterns, reveals unbroken sequences spanning thousands of years, including the supposedly phantom centuries. Samples from Chinese, European, and North American forests all sync up, showing no missing blocks of time. Even more damning, eclipse records from other cultures, like the meticulous observations of Chinese astronomers, perfectly match modern calculations with no 300-year gap. The real mystery isn't whether history was erased, it's why this theory persists despite overwhelming evidence. Perhaps it taps into our fascination with hidden truths, the allure of rewriting the past like a cosmic detective story. But the universe keeps its own clocks. In the rings of ancient trees, the paths of eclipses, and the silent rotation of distant stars, and they all tell the same tale: time marches forward, leaving no room for phantom centuries. Some legends are fun to entertain, but the weight of evidence speaks louder than conspiracy. The cosmos doesn't just keep time, it guards it, and no ruler, no empire can fake the rhythm of the stars. At the edge of our solar system, something doesn't add up. The Kuiper Belt, a sprawling ring of icy debris beyond Neptune, should teem with objects getting denser the farther out you go. But then, suddenly, it just stops. Around 50 astronomical units from the Sun, the number of Kuiper Belt objects plummets like a cosmic cliff edge. This isn't just a gradual fade out, it's an abrupt cutoff, as if someone drew a line in the solar system's sand and said, "No further." Astronomers call this boundary the Kuiper Cliff, and its existence throws a wrench into our understanding of how planetary systems form. If the early solar system was a smooth disk of gas and dust, why would debris vanish so sharply at this specific distance? One tantalizing possibility is the gravitational hand of an unseen world, Planet 9, a hypothetical giant lurking in the darkness. A planet 10 times Earth's mass could shepherd the Kuiper Belt's outer edge, sweeping up or flinging away smaller objects with its immense pull. But there's another twist. Not everyone's convinced we need a hidden planet to explain the gap. Some simulations suggest primordial instabilities in the young solar system's disk might have sculpted this cliff naturally, perhaps a gravitational tug-of-war between Neptune and Jupiter scattered material outward before stalling abruptly. Others wonder if the icy fragments simply weren't dense enough to form large objects beyond this point, leaving a stark emptiness in their wake. The mystery deepens when you consider Sedna and other detached objects, bizarre worlds with orbits so stretched they loop far beyond the Kuiper Belt. These outliers don't fit neatly into either theory, hinting we might be missing an even bigger piece of the puzzle. For now, the Kuiper Cliff remains one of the solar system's most persistent riddles. Every new survey, every distant speck of light detected in that frozen frontier could bring us closer to cracking it. Whether the answer is a hidden planet, forgotten physics, or something entirely unexpected, one thing's certain: the fringes of our cosmic neighborhood still have secrets to spill. Galaxies shouldn't exist without dark matter. It's the invisible scaffolding that holds them together, the glue keeping stars from flying apart. Yet lurking in the constellation Cetus, there's a ghostly galaxy that defies this cosmic rulebook, NGC 1052DF2. This strange, wispy island of stars spins so slowly that if it contained any dark matter at all, we'd see its gravitational pull at work. But the numbers don't lie. This galaxy appears to be flying solo, a cosmic rebel that somehow built itself without the universe's most abundant ingredient. When astronomers first measured its rotation, the results sent shockwaves through astrophysics. Stars on the galaxy's outskirts moved sluggishly, their speeds matching only the visible mass. No hidden gravitational hand was needed to explain their motion. That's like watching a car speed down a hill with no engine and realizing it shouldn't be moving at all. Theories erupted overnight. Maybe we'd misjudged the galaxy's distance, skewing the calculations. Or perhaps dark matter had been stripped away by a violent encounter with a neighboring galaxy. But the plot thickens. Further studies confirmed the initial findings. This wasn't a measurement error. Then came the real curveball. Another dark matter-deficient galaxy was discovered nearby, NGC 1052DF4. Suddenly, what seemed like a fluke became a pattern. Could there be an entirely unknown pathway to galaxy formation, one that doesn't rely on dark matter's gravitational crutch? Some theorists speculate these galaxies might be tidal dwarfs, born from gas torn free during cosmic collisions, material too ordinary to attract dark matter's embrace. Of course, not everyone's convinced. Skeptics argue that even if dark matter isn't directly detectable, its gravitational effects might still be hiding in subtle ways, like a shadow just beyond our instrument's reach. Others wonder if modified gravity theories, which tweak Newton's laws to eliminate the need for dark matter entirely, might finally get their moment in the spotlight. Whatever the answer, NGC 1052DF2 is more than an oddity, it's a challenge. A single galaxy playing by different rules forces us to question whether dark matter is as universal as we thought, or if the cosmos has a few surprises left in its back pocket. After all, the universe doesn't owe us tidy explanations. It just offers clues and dares us to keep up. Tucked away in the cosmic microwave background, that ancient light from the dawn of time, lies a chilling anomaly. Dubbed the cold spot, this patch of sky is eerily colder than its surroundings by a few hundred microkelvin. At first glance, that might not sound like much, but in the ultra-precise world of cosmology, it's a screaming red flag. This isn't just random noise, it's a cosmic bruise, and scientists are scrambling to figure out what left it there. One leading theory is as mind-bending as it gets. The cold spot might be evidence of a collision with another universe. According to multiverse hypotheses, our universe could be one bubble among countless others in an endless cosmic foam. If one of these bubbles briefly brushed against ours during the Big Bang, the energy drained from that encounter could have left behind a frigid imprint like a fingerprint on the fabric of spacetime itself. But not everyone's ready to jump to parallel universes just yet. Skeptics argue the cold spot could simply be a supervoid, an enormous, nearly empty region of space where matter is so sparse that light passing through loses energy, creating a cold shadow in the CMB. The problem, even the largest known supervoids can't fully explain the cold spot's extreme chill. The numbers just don't add up. Here's where it gets even stranger. Detailed studies reveal the cold spot isn't just cold, it's also surrounded by a peculiar ring of hotter-than-average plasma. That's like finding a frosty circle in the desert, ringed by scorching flames. Some researchers suggest this could be the aftermath of a cosmic titan, a collision between galaxy clusters so violent it sent shockwaves rippling through the early universe. Yet the mystery endures. If it's a supervoid, why is it so much colder than physics predicts? If it's a multiverse bruise, how do we test something so speculative? For now, the cold spot remains one of cosmology's most tantalizing Rorschach tests, a cosmic Rorschach test inviting us to project our boldest theories onto the universe's oldest canvas. Whether it's a flaw in our models, a glimpse beyond our reality, or something entirely unexpected, one thing's clear: the universe loves leaving its coldest cases unsolved. Deep in the quantum realm, where the rules of physics twist and bend, there's a theoretical wildcard that could rewrite our understanding of matter itself. It's called unparticle physics, a radical idea where particles stop behaving like particles entirely. Instead, they morph into something stranger, entities with no fixed mass, no predictable energy, acting more like ripples in an invisible cosmic pond than solid matter. The theory emerged from a tantalizing puzzle. What if dark matter, the invisible glue holding galaxies together, isn't made of traditional particles at all? Unparticles would operate outside the standard model's tidy categories, producing forces that don't weaken with distance like gravity or electromagnetism. Picture a shadowy substance that doesn't clump like normal matter but spreads like a mist, its influence defying conventional laws. For decades, physicists assumed dark matter must resemble the particles we know, just invisible and reluctant to interact. But unparticles flip that script entirely. They could explain why some galaxies rotate too fast without requiring vast halos of hidden mass. Instead, an unseen field of unparticle energy might subtly tweak gravity itself, bending the rules without leaving the usual fingerprints. What makes this idea so electrifying is its sheer audacity. Unlike WIMP or actions, the usual dark matter suspects unparticles wouldn't even have a defined size or location. Detecting them would demand entirely new approaches, hunting not for collisions in underground labs, but for faint anomalies in the way gravity behaves over cosmic distances. Of course, not every scientist is convinced. Critics argue that without experimental proof, unparticle physics remains a beautiful mathematical daydream. But its potential is undeniable. If real, it could solve more than just dark matter's riddles. It might unlock hidden layers of reality where the very concept of particle dissolves into something far richer. The cosmos thrives on mysteries that defy intuition, and unparticles are the latest dare from the universe to imagine the unimaginable where matter isn't what it seems and perhaps never was. Saturn doesn't just have rings, it has a six-sided secret. Floating atop the planet's north pole is a storm so precise, it looks like it was carved by geometry itself. This is the Saturn hexagon, a swirling vortex with 6 razor-sharp sides, each longer than the diameter of Earth. And here's the wildest part. It's been there for decades, maybe even centuries, defying everything we know about planetary weather. Hurricanes on Earth last weeks. Jupiter's great red spot has churned for centuries, but it's a chaotic oval, not a perfect polygon. Saturn's hexagon, though. It's like a cosmic snowflake locked in place, rotating with eerie precision. When Voyager first spotted it in the 1980s, scientists assumed it was a fleeting oddity. But Cassini's later close-ups confirmed the unthinkable. This wasn't a fluke. The hexagon had persisted, unchanged, for over 30 years. So how does a storm hold its shape against the violent winds of a gas giant? Lab experiments might hold the key. When scientists spin fluids at different speeds, geometric patterns emerge, just like Saturn's hexagon. The planet's jet streams, racing at over 300 miles per hour, could be etching this structure into the atmosphere, with deeper layers acting like an invisible guide. Think of it as a cosmic dance where turbulence and stability collide to form something impossibly ordered. Yet the hexagon still guards its mysteries. Why 6 sides? Why not 5 or 8? Some models suggest resonance, a harmonic effect where atmospheric waves sync up at specific ratios, locking the storm into this exact shape. Others hint at deep-rooted forces where the planet's rotation and internal heat sculpt the skies in ways we've never seen elsewhere. What makes this storm so mesmerizing isn't just its strangeness, it's the reminder that even in the chaos of space, nature finds patterns. Saturn's hexagon isn't just a weather phenomenon. It's a celestial puzzle whispering secrets about the hidden physics spinning beyond our world. And until we send another probe to stare into its 6-sided eye, it'll keep taunting us, a perfect shape in an imperfect universe. Venus has always been the solar system's cautionary tale, a blistering, toxic wasteland where lead would melt like butter. But in 2020, this hellish planet dropped a bombshell that sent astronomers into a frenzy. Traces of phosphine gas, a compound often linked to life on Earth, had been detected in Venus's clouds. For a fleeting moment, the universe seemed to whisper, maybe we're not alone after all. The discovery came from data so precise it couldn't be ignored. Using the James Clerk Maxwell telescope in Hawaii and the ALMA array in Chile, researchers spotted phosphine's spectral fingerprint floating about 30 miles above Venus's surface, a region where temperatures and pressures are almost cozy compared to the furnace below. On Earth, phosphine is mostly produced by microbes thriving in oxygen-starved environments like swamps or labs. So when it showed up on Venus, the implications were electrifying. Could airborne microbes be clinging to existence in those sulfuric acid clouds? But Venus doesn't give up its secrets easily. Almost immediately, skeptics pounced. Phosphine might not require biology at all. Volcanic activity or exotic chemical reactions could theoretically cook it up. Yet Venus hasn't shown recent volcanic proof, and known geochemical pathways struggle to produce phosphine in such quantities. The debate grew so heated that some scientists reanalyzed the original data, arguing the signal might have been misread. ALMA even recalibrated its instruments, though the phosphine signature stubbornly persisted, if fainter than before. Here's where the mystery deepens. Even if the phosphine is real, Venus's atmosphere is a gauntlet of ultraviolet radiation and corrosive acids, hardly a welcoming habitat. But extremophiles on Earth have thrived in equally hostile places, from boiling vents to nuclear reactors. Some theorists imagine microbes with sulfur-based metabolisms, floating in droplet havens high above the scorched surface. Others propose abiotic processes we've yet to discover, where Venus's unique chemistry defies expectations. For now, the Venusian phosphine remains an open question, a tantalizing what-if hanging in the clouds. Upcoming missions like NASA Da Vinci and ESA Envision could settle the debate by sniffing the atmosphere firsthand. Whether the answer points to life, strange chemistry, or something in between, one thing's certain: Venus just became the solar system's most unexpected thriller. And in the search for life beyond Earth, sometimes the most promising clues come from the places we least expect. Peering into the afterglow of the Big Bang, astronomers found something that didn't quite add up. The cosmic microwave background, the oldest light in the universe, should be a nearly perfect snapshot of the cosmos's infancy. with tiny temperature variations scattered randomly like static. But on the largest scales, those fluctuations mysteriously weaken. This anomaly, known as the CMB quadrupole moment, hints that the universe might not be as uniform or as infinite as we once assumed. Picture this: if the cosmos were an orchestra, the quadrupole moment would be the missing bass notes. On smaller scales, the CMB's temperature variations match predictions beautifully. But zoom out far enough, and the fluctuations grow oddly quiet, as if the universe itself is humming at a lower volume than expected. Some researchers argue this could mean space isn't isotropic, that it stretches differently in certain directions, like a rubber sheet tugged unevenly. Others wonder if the universe might be finite, curving back on itself in ways we can't yet perceive. Then there's the real head-scratcher, the axis of evil. This controversial alignment links the quadrupole's weakness to the same eerie solar system plane correlation seen in other CMB anomalies. Could there be a hidden cosmic preferred direction, a relic of the Big Bang's asymmetries? Or is this just a statistical fluke, a trick of the data that future observations will smooth out? The implications are staggering. If the universe isn't the same in all directions, it could force us to rewrite inflation theory, the idea that space expanded uniformly in its first moments. Maybe the early cosmos didn't stretch evenly after all, leaving behind subtle wrinkles in spacetime itself. For now, the quadrupole remains a whispered question in the cosmic static. But with next-generation telescopes probing deeper, we might finally learn whether this hush in the heavens is a clue, or just the universe reminding us how much we still have left to hear. The sun hides one of its most baffling secrets in plain sight, a blazing crown of fire that defies all logic, while its surface simmers at a mere 5,500 degrees Celsius, the corona. The wispy outer atmosphere we see during eclipses roars at temperatures over 1,000,000 degrees. It's like walking away from a campfire and suddenly feeling more heat the farther you go. This cosmic contradiction has puzzled scientists for decades, and the answer might rewrite how we understand stars themselves. One clue lies in the sun's magnetic chaos. Beneath the visible surface, tangled magnetic fields surge and snap, releasing energy in explosive bursts called nanoflares. These aren't your typical solar flares. Think of them as microscopic sparklers, each packing a minuscule punch. But collectively, they could be the corona's invisible furnace, dumping heat into the outer atmosphere like 1,000,000 matches lighting in unison. The catch: we've never directly observed a nanoflare. Their existence is inferred from the corona's seething energy, a ghostly handprint on the sun's fiery sleeve. Then there's magnetic reconnection, a process so violent it turns the sun's magnetism into pure heat. Picture two rubber bands stretched to their limit, suddenly snapping and releasing pent-up energy. On the sun, colliding magnetic fields do the same, realigning with a force that supercharges surrounding particles. Satellites like a Parker solar probe have glimpsed this in action, diving closer to the sun than any spacecraft before and capturing surges of energy where theory says they should be. Yet the mystery deepens. Some researchers argue sound waves, yes, actual sound, might play a role. Turbulence in the sun's churning plasma could generate acoustic waves that travel outward, dissipating their energy as heat in the corona. Others point to solar tornadoes, massive whirlwinds of magnetized plasma spinning at breakneck speeds, potentially funneling energy upward like cosmic thermometers. What makes this enigma so thrilling isn't just the science, it's the stakes. Unlocking the corona's heat could explain why solar winds batter Earth, how stars evolve, and even how to harness fusion energy. Every new mission, every daring probe that braves the sun's fury, peels back another layer of this celestial onion, and until we crack it, the corona remains a reminder. Even the most familiar star in our sky still guards secrets hot enough to melt our assumptions. Black holes dominate the cosmic horror show, unstoppable monsters that devour everything in their path. But what if they have an equally bizarre counterpart lurking in the equations of physics? Enter the white hole, a black hole's theoretical twin running in reverse. Imagine a cosmic fountain where matter and energy erupt outward instead of vanishing forever, a place where nothing can enter, only escape. The math is surprisingly solid. Einstein's theory of relativity allows for white holes as valid solutions, flipping the script on black holes' endless hunger. If a black hole is a one-way street into oblivion, a white hole would be an exit ramp with no on-ramp, spewing out particles and light that could never return. Some theorists even suggest that when a black hole dies, it might rebound as a white hole in some distant future, or in another universe entirely. Yet here's the puzzle: no one's ever seen one. White holes would be dazzlingly bright, ejecting energy at unimaginable rates, so why don't our telescopes spot them? One possibility is they're vanishingly rare, flickering into existence for mere moments before collapsing under their own absurd physics. Another wild idea: they might only exist in the early universe, flaring violently during the Big Bang's chaos before winking out of existence. Skeptics argue white holes are mathematical ghosts, tricks of the equations with no physical reality. But recent work in quantum gravity hints they might play a hidden role. In loop quantum cosmology, for instance, the Big Bang itself could resemble a white hole's rebirth, with space-time bouncing from a previous universe's collapse. Whether cosmic mirage or undiscovered wonder, white holes challenge our instincts about how reality should work. They're a reminder that the universe's rulebook might still have pages we haven't turned, and that even the darkest corners of space could hide bursts of impossible light. From black holes that vanish information to galaxies spinning faster than physics should allow, we've journeyed through 30 cosmic mysteries that defy everything we thought we knew. Each one is a reminder: the universe doesn't exist to follow our rules, it's out there rewriting them, one enigma at a time. These puzzles aren't just curiosities, they're the frontiers of discovery. Every contradiction, every anomaly, is a clue waiting to crack open the next chapter of science. Whether it's dark energy accelerating the cosmos or a storm on Saturn with perfect geometric edges, these mysteries push researchers to think bigger, dig deeper, and question the foundations of reality itself. So which one left you stunned? The eerie silence of the Fermi paradox, the interstellar oddity of Oumuamua? Drop your favorite in the comments. We'd love to hear what sparks your cosmic curiosity. And if you're hungry for more mind-bending space revelations, hit subscribe and join us as we keep unraveling the universe's greatest secrets. After all, the next breakthrough might be just one observation away. Until then, keep looking up, because out there, anything is possible.